So welcome to the next session of biomedical systems and mathematical models. In today's session we will talk about the two multimodal techniques, the first one being near infrared spectroscopy and the next is the ultrasound system, and how we can use both of these techniques to actually quantify the bulk properties of the tissue, such as in optical we have the optical absorption coefficient and optical reduced scattering coefficient, and in the case of ultrasound we have attenuation coefficient. So we will see how these bulk properties we can quantify from these extracted tissues from the breast. So as you can see on my screen, in the case of near infrared spectroscopy there are three different techniques where people use. The first one is the continuous wave near infrared spectroscopy, that is, you have the light which is passing through the tissue. So you give a light inside the tissue with a particular amplitude and it passes through the tissue. There is a certain decrease in the amplitude and you detect this with a detector, the light detector. It could be a silicon photodetector for example, or it could be a photomultiplier tube. But in the case of continuous wave you can use this silicon photodetector itself. When you go ahead to even higher frequencies, for example in order of megahertz or so, where you are able to distinguish between the phases of the different tissues. So in that case we are not giving a continuous signal to this tissue, but now we are going to give a sinusoidal input to the tissue. So what we have is, if this is a tissue for example, we have the LED placed on top of it which gives the light, we shine the light, it could be a LED or laser, it shines the light on the tissue, and then after it propagates through the tissue we detect it using a photodetector. Okay, so this is the source and this is the detector. So in the second case we use a sine wave or a harmonic input to excite the source. Okay, and after it passes through the tissue you can see there are two things. The first thing is that the intensity has now reduced. So this will give you the information about the attenuation of this light intensity, and second is the phase difference of the initial and the observed response of the photodetector. Okay, so there would be some phase difference between the actual input signal and the signal which has been detected after it has propagated through the tissue, and this phi over here, so this phi over here can help you calculate the scattering coefficient. Okay, this reduction in the amplitude will help you to get you the absorption coefficient. Okay, so these are the bulk properties with which you can actually quantify with the frequency domain simulation. In the case of time domain simulation, as you can see in the C part over here, instead of giving a sinusoidal input we give a pulse which is of very small duration, which is in order of picoseconds ideally. Okay, and once it passed through the tissue, so you can see that as you have already seen in my earlier lecture, as the light passes, or the photons actually which passes through the tissue, it goes under a large number of scattering before it passes through and goes through this tissue. There are some photons which are having more scattering, and there are some tissues which are having less scattering. So some of them which undergo less scattering, they reach very quickly. So these are these photons which reach very quickly, and then there are some photons which scatters very high and they reach very late to the detector. Okay, so there what you observe is not just a rectangular function, but you see some kind of a Gaussian peak which with a long tail. So you see that the tail is stretched out on the one side, and from there you can actually quantify so how much is the stretching of this tail. From that you can quantify the scattering coefficient, for example. So if there is more stretching of this tail, which means there is more scattering, which means you can quantify the scattering coefficient. Again, you can quantify the amplitude of the received signal, and from there you can quantify the absorption coefficient. So there are different techniques which you can use to quantify the different bulk optical coefficients, such as absorption and the reduced scattering coefficient. So let us come to this system that we developed at IISc. So this system is a spectral IRDX system, and this we incorporated only near infrared spectroscopy technique earlier, that is a transmittance based near infrared spectroscopy, but we updated this system with a multimodal technique, that is now it is having the capability to quantify both the ultrasound as well as the near infrared spectroscopy. So let us go into these topics one by one. The first topic is the ultrasound. So what you see over here is this assembly, where this is the sample, where the sample needs to be kept, okay, and the other regions actually are for the placement of the technology or the modules. For example, in this case we have the ultrasound module, and second we will talk about the near infrared spectroscopy module. In this case what we do is we keep the ultrasound source. So this is a piezoelectric sensor, okay, as you can see over here. So this is the piezoelectric sensor, the same piezoelectric sensor, and then we have the coupling medium. So there is the ultrasound transducer, which incorporates a piezoelectric sensor. It gives an ultrasound waves which passes through the medium, and then it passes through the sample, and then it again passes through the medium and gets detected by the detector over here. So this propagation through the combination of medium 1, coupling medium, sample, that is a tissue sample, and again the coupling medium is being provided over here. The coupling medium is required because you need to have low impedance between the coupling of ultrasound transducer and the sample, tissue sample. So they have a different impedance. So to minimize this reflection due to impedance mismatch, we use the medium, a coupling medium, and this coupling medium needs to be again be used once you want the ultrasound wave to propagate from the sample to the detector, and that is why we need this coupling medium over here. In this case we use this coupling medium, which is proprietary of the company with which we bought the ultrasound transducer. What we do is we actually give impulses, short pulses in order of few hundreds of nanoseconds. So for example, 500 nanoseconds we observed. At 500 nanoseconds there was a very good delineation between normal and cancer tissues. So we propagate very short pulses of ultrasound input from the source, and which passes through this through these mediums, and what we observe is that we get a signal like this, similar to what we observed in the time domain analysis of the near infrared spectroscopy, but this is a case of the ultrasound technique. Okay, so the actual experiment system looks like this. So this is the first ultrasound transducer which acts as a source. This is the coupling medium. This is the actual sample. This is again the second coupling medium, and then finally we have the detector, ultrasound detector. You can see the detected wire, the wire which is coupling this detected ultrasound is actually shielded, so that there is very less EMI interference between the input and the output signals over here. So this is the case of the ultrasound detector. So let us go ahead with the continuous wave near infrared spectroscopy. To quantify the absorption and the scattering coefficient in the case of near infrared spectroscopy, people have already used the double integrating sphere approach. A double integrating sphere is what you see in the bottom over here. So it involves two different spheres which are connected to each other through this input and exit ports over here. You keep the samples somewhere over here, okay, and your LED light is over here, and you shine this light through the tissue which actually back scatters as well as forward scatters, okay. And the same thing you can see over here in the schematic, okay. You so if I do the cross section and view in the schematic over here, what you see is the source is placed inside the center, and then this is the tissue sample, and which scatters the light both backward as well as forward scattering, okay. This light which interacts with the inner surface of this sphere, which again gets diffused scattered, okay, and this diffuse scattered light is then scattered again. So this light which comes over here, which again scatters over here, and then there is again a diffuse scattering which is taking place over here, and goes through multiple diffuse scattering with very low losses or less absorption, and finally it actually gets detected by the detector. So we assume that there is a very low loss after it gets hit by the surface over here. The same case happens once it gets the light which is actually going through this forward scattering. So it goes to the forward scattering, and what you see is again the light gets diffusely scattered and then gets absorbed by the detector, okay. So we get the detected voltage 1 from the first detector and detected voltage 2 from the second detector, and then we can use this to actually quantify the bulk optical properties such as mu A and mu S, okay. And the bottom what you see is the actual experimental setup where you have this detect. So this is the, again we cut slice this open the integrating spheres, and this is the top view, so this is the bottom view in the top, and then we have the side view over here. So what we see from the bottom view is that this is the detector, first detector, this is the second detector, and this is the baffle, so that there is no direct interaction from the light which is getting scattered to this detector. So only the diffused light should actually go through this detector. What you see over here is this LED lamp, LED light over here, and this is this tissue sample over here, and yeah, so you can see that the inner surface of this integrating sphere is actually coated with barium sulfate. Barium sulfate has the property to reflect 98% of the near infrared light which is incident on that particular surface. And as the name suggests itself that it is actually a integrating sphere, so it integrates the light which gets scattered from the tissue from all the sides and it gets detected by the detector, okay. So let us go through the mathematical model which requires to be used to quantify the acoustic coefficient and the optical coefficients. The first is the acoustic coefficient. In the first case, what you observe is what we give an input is the pulses over here. So it's a voltage pulse which is 5 volt peak to peak to the ultrasound transducer, okay, and having a VDC of around 2.5, right. So this is actually 0 volt, the bottom part. So to quantify the acoustic attenuation coefficient, we come up with two different cases. The case 1 is the we assume that the reference medium is there in the center. In the case 2, where we assume that the sample is the actual tissue sample is there in the center domain, okay, instead of the reference medium. Okay, so we have the voltage detected with this reference medium and the voltage detected using the sample tissue both. In the case of reference medium, in this case the reference medium is the same as the coupling medium. Over here we actually can calculate the detected voltage. So this is the detected voltage over here as a product of transfer function of the system and the product with the exponential of minus alpha naught x, where x is the total distance over here. So if over here you can see this is the x, that is the complete distance from starting from the medium 1, the tissue sample or the reference medium, and the medium 2. So this is the x, the total distance over here, and alpha naught is the attenuation coefficient of the reference medium. Okay, this alpha naught is the same for medium 1, reference medium, and medium 2. In the second case, with the tissue sample you have a different equation that represents. So you have RT, and then there is a product of two terms. The first term is for the coupling medium. So this is for the coupling medium, and second is that is xm, that is the thickness of the sample medium, and this is for the sample tissue. Okay, so for the medium, coupling medium, the attenuation coefficient is alpha naught, and we know this alpha naught, while for the sample tissue it is assumed as alpha over here, but this is what we don't know. So we still don't know what is alpha over here, that is the attenuation coefficient of the sample tissue. We know the alpha naught of this coupling medium 1 and coupling medium 2, but we know the rest of the values. So for example, we know this x, we know the xm. So let us see how we come across and how do we calculate this alpha from these other equations. So now if we have the two equations we mentioned over here, equation 1 and equation 2, we can take a ratio of them and we can do away with this transfer function which relates this experimental setup. So that actually goes, so RTF actually goes away, and we have only the exponential of minus alpha naught xm times the transmission square. The transmission is the transmission coefficient is actually we can assume it to be 1 in the case where we assume that the acoustic wave propagation is transmitted completely from the medium 1 to the sample tissue, for example, and from sample tissue to the medium. Okay, so this is an assumption over here. So if we assume that the transmission actually approaches 1, in that case the equation can be simplified to this equation over here, and in this case all of the components are known. For example, V alpha, Va is known, Vb is known, alpha naught is known, xm is known. The only unknown is the alpha, that is the attenuation coefficient of the sample tissue. So we do multiple experiments, we repeat it for 3 times, and we then quantify the average alpha value for each of the sample tissue. Now let us go for the near infrared spectroscopy mathematical model. So what do we have over here is the double integrating sphere, as we discussed earlier, and the light which gets back scattered from the tissue gets detected by the detector 1. So you get the values of detector 1 and you get the values of the detector 2. These two values of voltage, that is VD1 and VD2, are performed for different tissues, and from there you come up with the value of MR. MR is the is the measurement reflectance and MT is the measurement transmittance. And the equation over here represents the different cases. For example, the first one represents for the actual case, like what you detect over here. So your R of R comma T is for the detector 1. Over here, this one, the T of R comma T is for the detected one, that is transmitted. Similarly, if you remove the sample over here, and keep this port empty, you get this value, okay, from the detected one. And if you remove the sample over here and you calculate the transmitted power, you get this T naught value. So from this MR and MT value that we get, we input it into a Monte Carlo method over here. So that is inverse adding the doubling software that we used over here. So yes, mentioned over here, and the reference is also mentioned. So it's from S. Prahal in the center, in the bottom you can see it. And this software is available freely on the internet. You can download it and use it. What we need to mention is the diameter of this of the spheres, equal spheres, the refractive index of the tissue you need to mention, and once you mention this, you also need to mention this wavelength, that is operating wavelength. In our case, we measured it for 850 nanometers, 940 nanometers and 1060 nanometers, and from this we quantified the absorption coefficient and the scattering coefficient. So you input these values in this software and you get this mu A and mu S prime. So this is how this transient ultrasound response looks like, okay. So over here you can see this in the case of normal, so you can see the blue curves are for the normal and the red one are for cancer, and P actually signifies the paraffinized embedded tissue sample. So there are different ways to store the tissue, whether it could be either paraffin embedded, which needs to be deparaffinized, and second is the F, you can see. So the F is actually stands for this formalin fixed tissues, okay, the second letter that's just over here. So in the case of normal tissues, you can see that the amplitude of the response is very high as compared to the cancerous tissue. So what is you can see is that the cancerous tissue have are able to absorb these signals, time domain acoustic ultrasound response very quickly, but in the case of normal, it's able to allow this ultrasound radiation to pass through the tissue. Same is the case seen in this formalin fixed tissues. Here N stands for this normal, adjacent normal, F stands for this formalin fixed, and C actually stands for the cancerous tissues. So you can see that normal tissue has very high amplitude of signal. Please note that the input that goes into the system is this pulse, which is having 500 nanosecond pulse, okay. So this is a system which goes through this tissue, give this pulse of ultrasound to the tissue, and what we detect is the results that you see over here, okay. From this we quantify this attenuation coefficient over here, okay, and what we see is that for cancerous tissue the attenuation coefficient is like very high as compared to the normal tissues. We also observe for the fibroadenoma the attenuation coefficient is higher than this normal tissue, and for the cancerous tissue it's even higher for as compared to the normal tissue. And for this there was a clear delineation. If you use this factor or this value of around 13 dB per centimeter, you can easily distinguish between normal and cancer. In the case of near infrared spectroscopy, we did it for 3 different wavelengths, that is 850 nanometers, you have 940 nanometers and 1050 nanometers. So here you can see that there is a very good delineation in the case at 940 nanometers for both between normal and fibroadenoma tissues and normal and cancerous tissue. In the case of 850 nanometers, we can see that there are good delineation between normal and cancer at 850 nanometers, but not so much for 1016 nanometers. So not much in the case of 1016 nanometers over here. Slight significance at between normal and cancer at 1060 nanometers over what you can see over here. So this is what we have observed when we perform this multimodal. Multimodal is known as because we combine the acoustic measurements or the ultrasound measurement along with the near infrared spectroscopy measurements. So that's it with this session. The next session we will talk about another technique which we use to quantify the thermal properties of the tissues